Yeah. So, hello again. So this is the, now we're gonna do some applications of the Cauchy formula. Well, really one application of the Cauchy formula. So we're looking at section 3.3.1 or subsection 3.3.1. All right. So this is a big consequence of Cauchy's formula, right? It's one of the really big things, right? We saw that analytic functions, things with a power series, have lots of nice properties, but we haven't been able to, just immediately say that, well, holomorphic functions are, have all these wonderful properties, and vice versa. Holomorphic functions have some properties that might be hard to prove for analytic functions, right? For just using the power series, for example, we haven't proved. We haven't even proved that a convergent power series at one point is analytic, right? Because it's just if we have a convergent power series, right? It's convergent when written as a power series at one point. How do we know that function, that's the limit, can be written, can have a power series expansion around other points, right? That's maybe not so immediate, right? It's true, and this will, this will show it, because we've proved that a power series defines a holomorphic function, right? But even something like a composition of analytic functions is analytic. If you try to do it, try to think about how, if you're plugging in a power series into another power series, there's a bunch of limits that you need to swap, right? So that doesn't seem so trivial. But holomorphic function, yeah, it's simple. That's just the chain rule. Chain rule is easy to prove, right? So we'll get sort of cross-pollination, right? Anything that we proved for holomorphic function is true for analytic function, and vice versa, right? So, we've already proved before that analytic functions are holomorphic, as I mentioned, right? Power series are holomorphic, therefore analytic functions are holomorphic, right? Because that was a stronger definition than just being a power series. So now we prove the converse. We prove that if we have a holomorphic function and we pick a random point, then that the function has a power series expansion around that point. All right, so let's write down what the theorem is. Right, so I have any open set. I have any holomorphic function, any point inside, and any disk, and this is going to be actually. This is a big thing over here. I'll say more about it again in a bit, right? Any disk that fits in U, right, around phi, right? So centered at p, but any disk that fits in U, right? So you can just take the largest one, right? You can just take the supremum of R, if you could even take the complex plane if U was the complex plane, right? This would work with the complex plane, although then it wouldn't be a disk, right? But then any disk would work, right? Okay. Then there exists a power series, right, such that for all z in this disk, we get convergence, right? We get this formula, right? So this power series will have to converge for, inside this entire disk, right? And the only, we haven't, estimated anything, right? It's just, the whole, the function is just holomorphic on this disk, right? That's really the only thing that, U could be even equal to this disk, right? But that's the only thing that we assume, is just that this disk is inside U, and we get not only that F has a power series that converges to it, it converges to it on this disk, right? Oops, what's happening? Oh, yeah, there we go. Right, so it it has this this formula. Moreover, right, we don't just prove that these CNs exist. We give a formula for them, right? We have an explicit formula for these CNs, right? I can get them just by taking any circle of radius r. I mean, there's going to be even more formulas, but what we're going to prove directly in this in this next proof is going to be, well, take any circle of radius r, right? Call it gamma of little r, right? It has to be inside this disk so that I could integrate over it. Centered at p, oriented counterclockwise as usual. I integrate this this thing that sort of looks like the Cauchy formula, except there's the n+1 here, right? So C naught would be the thing with, well, where n was 0, right? So that would be like the Cauchy formula. That would give you, the Cauchy formula would give you f of p, and yeah, we know that that's true, right? I mean, the first coefficient of the power series should be the value of the function at that point, right? So yeah, I mean, it definitely works there if if this is true, if this power series exists, right? So, and it is going to be a consequence of the of Cauchy's formula, right? So it makes sense that it sort of looks like Cauchy's formula, right? So let's prove this. Right, so let's fix such an R, right? Just any little R inside this big disk, right? And so from that, that wasn't true for this big R. The reason really for doing that is so that we have the whole closed disk, including the boundary, is in our U, right? It's actually in our big disk, right? Inside, right? So we can integrate over it. All right, so let's fix a z inside this small disk, right? Smaller disk, right? It doesn't have to be very small. It could be very big. It could be little r could be almost as big as r, right? Now, if we have if zeta is going to be some complex number on the boundary of this disk, so on this what we're going to call gamma, right, or what we called gamma in the term, then, well, it's precisely distance r from p, right? So if we look at, maybe this is going to be right now, it sort of seems like it's just pulled out of thin air, right? If we look, you'll see it in a moment why we're looking at this. Z minus p over zeta minus p. Well, the bottom, that's just r in modulus. I'm taking the modulus of this whole thing, right? So it's really z minus p over r. Now, z minus p is less than r because z is inside the disk. So this guy over here is strictly less than 1, right? Now, right now it might seem, I'm just pulling it out of thin air, but this is where it comes up. If I take the geometric series, well, maybe it still seems a little bit like I'm pulling it out of thin air, right? Why am I taking this geometric series? We're gonna see it in just a moment. So if I take these guys and I write down the geometric series, in these guys, right? Well, this thing converges, right? And it converges to this, right? That's just writing down the geometric series and doing a little bit of algebra. I get this. It's sort of kind of it looks like something from the Cauchy formula, and that's on purpose. So not only does it converge, I mean, it converges uniformly, absolutely, because this estimate, right? If z is fixed, right? So this is a fixed number. This is always r, right? So we get it's bounded by this number which is, which doesn't depend on zeta, right? So this is actually uniform. This converges uniformly, absolutely, for zeta in the boundary, right? All right. So so let's write down the Cauchy formula, and again, notice this thing, over here. That's going to be important. Right. So what I'm going to do is I'm going to take that and use this, this expression over here to sort of pull it out, separate it from the f of zeta, right? So I have f of zeta minus p, right? Well, zeta minus p, so I have to cancel out, right? So that's all I did over here, right? But now I have it sort of separated as two pieces. One of them doesn't depend on z, and the other one is this thing that I have a series for. Power series for that converges really nicely. So let's write down this is equal to this into this formula. That's what I do here, right? So this equals this over here, right? That's what we did. Okay. So that's that's starting to look good, right? Why? I have over here there's nothing that depends on z. The only thing that depends on z is really these terms over here, which do look like the terms I'm getting in the power series, right? Z minus p to the n. That's what I'm getting over there, and everything else is going to be sort of coefficients in this series, right? There's no other z dependence, so it's starting to look like a power series, and that's what happens, right? Now, let's, whenever you see two limits, you swap them and see what happens, and then you then you check, was that allowed, right? So we have to still justify that this equality, right? But this this limit over here, can I swap it with this integral? Now, if I could, I get this, right? Moving things about a little bit, right? I get this term goes here, right? Those are my powers in the power series, right? Then I have nth power of zeta minus p and another one over here. That's why I'm getting the n plus 1 powers, over here, right, in the denominator, right? And the rest is just, I'm just going to put it inside. Now, the point is, if this works, well, here that's RCN, right? So if everything converges and we were allowed to do this swap, that's RCN, right? This is the gamma over here, right? So we'd be basically done if we can justify this, swapping these two limits, right? The integral and the limit in the series, right? And that follows from uniform convergence, right? That we know that this convergence is really nice, right? It's uniform absolutely in the variable that we're integrating in, right? So let's see the details of that, right? So if we have if z is fixed, right, and it is, then or we can make it fixed. Let's put it that way. Let m be the supremum of this guy over here, right? The thing under the integral over there, and this bottom, right, zeta minus p is just r, right? So that's just, it's really just the supremum of the modules of f of zeta divided by r, right? And the boundary of this disk, right? We're taking zeta, on the boundary of the disk. That's what we're integrating. That's where zeta is varying. Well, that's a compact set. This has a supremum, right? It's a continuous function, right? So so if I write down the thing that's under the integral, right, the whole thing, I get this, and you know, that's inside the it's a term of the series, right? So the whole series is under the integral, right? But these are the terms of that series, right? And I write them out like this, and this inside I have, well, let's just less than 1, right? I mean, we saw that before, right? So I have, this is not 1. There's this m, I can just take out, that's just this, right? So I have that the insides of this series are, the terms are bounded by this, right? Where each one of these powers is less than 1. And over here, there is no z dependence, right? Not the zeta dependence, right? So this is uniform in zeta, right? That's the point, right? Uniform in zeta, right? So therefore, this thing, not just right? I mean, it's basically exactly the same as before. This thing converges uniformly in zeta, right? So the whole thing converges uniformly, absolutely, right? And we've proved that if we have a series that converges uniformly, absolutely, it converges uniformly, right? Again, if you remember the definition, it's not immediate, but it's very quick, right? If I have that this thing converges uniformly, then this thing converges uniformly, right? Uniformly in the zeta, that's what I need, right? That's what I'm integrating over, right? Right. So that's why we could have swapped the two limits. Let me go back to this. So that sorry, you can see what we're. Maybe let me get rid of this. Right. You can see. I mean, the limit over here. Right. We need this thing over here. Right. To converge uniformly in zeta. Right. I mean, that's a limit over there, right? To be able to take it past here, right? Past an integral in zeta, right? And that's really going. I mean, it's really not in zeta. It's in some whatever the parameter is, right? And it's going over a compact interval, right? T is maybe going from 0 to 2 pi or something like that, right? And so, if I have a uniformly convergent sequence of functions that I'm integrating over a bounded interval, right, I can swap the limits, right? So let me go over here. So we found a power series for f at z, and it works for any z clearly, right? So therefore, it's analytic, right? Now, by uniqueness of power series for any particular z, the Cn are independent of R, right? I mean, the Cn, once you have a convergent power series, it has, you look at the limit. We know that we've proved when we looked at power series that the coefficients are unique, right? So no matter how you computed them, right, you're going to get the same numbers, right? So no matter what little r was, you have to get the same numbers, right? Even though that is a different expression, right? The one that we looked at, right? The one in the theorem for the Cn, but it has to be the same, right? Because of uniqueness of power series, right? So therefore, we're done, right? It worked in any R. Now, this was for all z in the small disk, but now we said we actually get the same power series no matter what R was, right? And therefore, we have to get the same power series for all z in the big disk, right? In the capital R disk, because you can just always pick a, if you want it to be converge in a slightly different, slightly different point, one that's closer to the boundary. Well, pick a large or small r, right? Little r that's closer to capital R, so that your z is inside. Now you get some series, and it's the same one, right? That converges over there, right? So it has to be there. There's only one series for this, right? And it converges in any disk of radius little r. Therefore, it converges in a disk of radius capital R. Okay, so what was the key thing in the proof? And this is actually sort of a common technique. So let's mention it. There's a common technique embedded in it. So the point is to take the Cauchy kernel, take the thing that you're integrating against. So you're taking f of zeta and you're integrating against this function. That's what's called the kernel. Sometimes you put the 1/2 pi I in there and you call that part of the kernel or not. It doesn't really matter. That's just bookkeeping. But that's the function that you're integrating against. Now the whole point was of writing it in a slightly weird way, writing it like this, so that you could write out the series for this second half of it over here, right? And that series for the second half is a power series in the right sort of things, right? So. And so this is the common technique, right? It's basically you write down a function, right, as an integral of something against some kernel, and then this integral, this new thing. In this case, it's the same function actually, gains some of the properties of the kernel. In this case, it gains the fact that, the kernel, it's really just a geometric series in some sense, and so the kernel has a power series representation, and the integral gains this property, right? And because f is equal to the integral, right, it also gains this property, right? So if you're going to write things as an integral against a kernel which has some nice property, a lot of times the integral gains properties from the kernel, right? This is useful in other places. In like, let's say that for example, at the heat equation for in partial differential equations, you write down the solution as an integral against the heat kernel, and the solution gains smoothness independent of, you might have started with a really, really rough initial data, right? Whatever your initial temperature is, the heat kernel is really nice, it's smooth, and the integral against the heat kernel gives you smoothness. So this is used all over the place. So in this case, we were interested in the function having a power series, right? All right, now let's again notice this other thing that I was yapping about for a while, that we didn't just prove that the thing is analytic. We proved something about the radius of convergence of these series. There's, if we have a holomorphic function in U, right, and we look at a point, we didn't just prove that there is some disk in which you have a convergent power series which converges to the function. We proved that it is actually the largest disk that fits in U, right? It always converges in that largest disk, right? If you think about it, if you think about the estimates that we got for convergent power series, right? The power series, the coefficients are the derivatives, right, of the function, right? You can get all the coefficients by the derivatives. Now we actually see that we can get them by integrals, right? So you get them by integrals, you can get them by derivatives, right? So they're derivatives of the function at p, right? So if you know how, what happens to the derivatives as to the nth derivative as n goes to infinity, right? What's the behavior of that sequence of, sequence of numbers? Then, that's what convergence, that tells you the radius of convergence, right? So the larger the radius of convergence, like these numbers have to be smaller, right? I mean, if you get, if the radius of convergence is infinity, you have to have that these numbers have to go to zero really fast, right? And so on, right? Something like that, right? You know the rate of growth. Or the rate of decay of these guys, depending on this r, right? So here we know something about the derivatives, about all the derivatives of a holomorphic function, right, at a point p, just depending on how far away from p the function is still holomorphic, right? So just because I get that the function is, doesn't blow up or do something weird in this whole disk, I actually know, how bad the derivatives get over here, or how good they are, right? So, for example, if the function had to be, also holomorphic in the entire complex plane, then I know that these go, the derivatives, the nth derivative at a point, as n goes to infinity, those guys have to go to, go to zero really, really fast, right? The coefficients have to go to zero really fast, right? So, right. I mean, then there is an n factorial. Sorry, right? So it's not that, it's the derivatives, how is it? Cn is the derivative over the n factorial, right? So that's what has to go to zero really fast. It's the coefficients, right? But those are given in terms of the derivatives. So I know something about the size of the derivatives, depending on how far away the function is still holomorphic, right? So nothing like this is true for real analytic functions. So real analytic functions are functions, just let's say on the real line, which have a power series in the real variable converging to this function. So for example, if I look at this function 1 over 1 plus x squared, around each point x on the real line, I can find a power series. This guy is defined on the entire real line, so it's analytic as far as the eye can see, as long as I'm only plugging in, by the way, as long as I'm only plugging in real numbers, right? So this is real analytic everywhere, but the radius of convergence at the origin, you can check, is only 1. It doesn't, the power series converges in an interval from -1 to 1 if I write down the power series at 0, but not not everywhere, even though the function is defined in the entire real line. Now the point here is that maybe a point, one of the points is I could, this expression over here, I can just plug in complex numbers, right? I mean, 1 over 1 plus x squared, I could just make the x's complex numbers. I could make them z's, right? So 1 over 1 plus z squared, right? And then this thing is not holomorphic in the entire complex plane. This thing is holomorphic except at plus and minus I, right? Because that's where this z squared, right? I squared is -1, so this thing is going to blow up, right? So if I think of this as a as a holomorphic function, as an analytic function in the complex plane, you see that it is not actually holomorphic at plus or minus I. And so if I look at the power series at 0, right, at the origin, the largest disk that I can fit into the domain of definition of this thing, where I'm replacing x with z, well, the largest disk that I can fit in is 1, right? So I can actually, just from that, I know that the radius convergence is going to be 1 without having to, try to do some sort of limit of n through it or whatever, right? So I know what the radius of convergence is, right? Which is kind of neat, right? All right, so let's restate, well, one of the main conclusions, but the thing that we started with, it's that the function is holomorphic if and only if it's analytic, right? So a function has a complex derivative at every point if and only if it has a power series representation near every point, right? So those two things are equivalent. That's what we can say now. So everything that we know about holomorphic functions, applies to analytic functions and vice versa, right? So as I said before, for example, the composition of holomorphic functions, that's easy to prove that it's holomorphic. It would be harder to prove for analytic. I mean, it's possible. It's not that bad, but it's much easier to just say, well, if you have it for holomorphic functions, because it was just chain rule, holomorphic functions are analytic, and you're done. Nice. I said that already, right? So we don't have to do this sort of, all that manipulating the power series. And as a sort of bonus, we finally proved that thing that I said that we'll have to wait for a little bit, right? That convergent power series actually defines an analytic function, right? So, for example, when we define the exponential, right? So originally when we define an exponential, we define it in the real exponential, in terms of real exponential and sine and cosine. Then we defined it as a power series at the origin. By basically using the power series method for solving differential equations, and so that was, and it was, so we got still got that it was holomorphic, but we didn't quite have that it's analytic. So now it's analytic also, right? Because we have a convergent power series is holomorphic, and therefore it's analytic. Therefore, it has a power series expansion around other points. All right, so that's good for this lecture. So let's stop. Well, if I can open up this this panel over here.